The objective of the paper plane Taguchi experiment are to identify the best control factor combination to maximize paper plane flight distance, to evaluate performance against noise factors indoor versus outdoor, male versus female, to guarantee dependable result under varying conditions, to apply Taguchi's method in analyzing how each control factors influence the performance of the paper planes. For the introduction, paper planes model real-world aircraft aerodynamics, experiencing lift, drag and thrust. This introductory study applies the Taguchi method to determine how plane design, paper thickness and added weight influence flight distance. By incorporating environmental conditions indoor versus outdoor and thrower gender as noise factors, we evaluate design robustness to achieve maximum performance under varying real-world conditions.
For theory, the plane design dictates lift and drag, while paper thickness and added weight control the balance and structural distribution. The Taguchi method used orthogonal array to reduce the number of experimental trials while maintaining reliable statistical analysis. Analyze data trend to pinpoint the ideal combination that maximizes flight distance while minimizing performance sensitivity to environmental
study. So the Taguchi method effectively optimizes design parameters and maximizes experimental efficiency while drastically reducing the number of required trials without sacrificing statistical reliability. It achieves this by identifying the best combination of control factor to deliver optimum performance with minimum variation. Consequently, this study applies the method to determine the ideal parameter combination for the longest and most consistent paper airplane flight distance. Research methodology. Our research methodology began with selecting 15 different paper airplanes designs. Each design underwent a screening test with 3 throws. Based on the results, the top 3 performing designs were selected for further experimentation. Next, we prepare the materials, which included standard paper and paper clips. Then design the experiment using the Taguchi L9 experimental design. Flight tests were conducted in both indoor and outdoor environments. Finally, the flight distance data were collected and analyzed to determine the optimal parameter combination.
The experiment was carried out following the L9 experimental arrangement. The selected paper airplane design were folded using the same folding procedure. Different paper thickness, which were 60 GCM, 70 GCM and 80 GCM, were prepared, and the required number of paper clips was added according to each experimental run. Each paper airplane was flown and the flight distance was measured using a measuring application on a mobile phone. The experiments were conducted in both indoor and outdoor environments to evaluate the effect of different conditions. By following the same procedure for every trial, we ensured that the collected data were consistent and suitable for analysis using the Taguchi method. Initially, our group created a total of 15 different paper airplane designs, with each member contributing several designs. Each airplane was thrown 3 times and the average flight distance was calculated to ensure a fair comparison. Based on the screening result, we selected the top 3 designs that achieved the longest average flight distance. These designs were Design 1, which is the blunt nose, Design 2 the pointed nose, and Design 3 the heavy nose. These 3 designs were then used as the design factor level in the Taguchi experiment. After selecting the 3 best designs, we planned the experiment using the Taguchi method. We considered 3 control factors, which were the paper plane design, paper thickness, and added weight using paper clips. Each factor consists of 3 levels. We also included 2 noise factors, which were the testing environment, either indoor or outdoor, and the thrower gender, either male or female.
For our project, we optimized paper plane flight distance using a Taguchi L9 orthogonal array evaluating design, paper thickness, and added weight. Looking at our factor effect graph, our optimal parameters to maximize flight distance are clearly identified as Design 2, which is the pointed nose, at 14.40 dB, next to, which is 70 GSM paper, at 13.39 dB, and weight 1, which no added paper clips, at 14.40. Our data showed that adding paper clip introduced severe dead weight, causing performance to drop sharply. Aerodynamically, the pointed nose cut through the air resistance more efficiently than the other design. As shown in the percentage influence chart, added weight is our most critical driver, accounting for 49.40% of the variant, followed closely by design at 43.81%, Together, these two factors dictate over 93% of the flight performance, which paper thickness play minor role at 14.65%. To validate this, we run a physical confirmation in experiment using the optimal settings and achieve an excellent 47.55% experimental error compared to our theoretical predictions. The Taguchi method was successfully proved that eliminating dead weight and maintaining a pointed nose geometry are the definite key to maximum flight performance.
For the discussion, this experiment applied the larger the better (LTB) approach to maximize the flight distance of the paper airplane. The overall mean obtained was 11.81 dB. The optimal parameter combination was designed to, which is the pointed nose, 70 GSM paper and no paperclip, as the setup produced the best flight performance. The pointed nose reduced air resistance, while 70 GSM paper provide a good balance between strain and weight. Adding a paperclip increased weight, which negatively affect the flight distance. Based on the sum of squares analysis, weight was the most influential factor at 45.58%, followed by design at 40.61% and paper thickness at 13.59%. In conclusion, the Taguchi method successfully optimized the flight distance of the paper airplane. The best combination was designed to with a pointed nose, 70 GSM paper and no paperclip. Among all factors, weight had the greatest influence, followed by airplane design, while paper thickness had the least effect. Overall, the objective of the experiment was successfully achieved. For future work, using a mechanical launcher is recommended to reduce human error and improve result consistency.